Galaxies are not the isolated islands they appear to be. They are connected by vast, invisible rivers of matter and energy that have guided their evolution for billions of years. These are the intergalactic filaments, the cosmic scaffolding that orchestrates the destiny of entire galaxy families. Think of galaxies as cities, and filaments as the superhighways delivering the raw materials for growth and interaction. By the end of this journey, you will understand the hidden architecture that binds our universe together. We will uncover how these faint threads determine where stars are born and why galactic clusters gather in specific patterns. What does it mean for our own Milky Way to be a traveler on one of these cosmic roads? The universe organizes itself with a breathtaking precision, forming a grand design known as the cosmic web. This is not a random splattering of lights, but a carefully woven tapestry, where brilliant clusters of galaxies gather at the intersections of faint, glowing strands. These strands are the intergalactic filaments, the true architects of cosmic structure. They act as immense bridges, constructed primarily from the mysterious fabric of dark matter and threaded with diffuse clouds of hydrogen gas. These filaments stretch across unimaginable voids, connecting galactic cities and entire superclusters in a continuous flow. For decades, their existence was a theoretical prediction, a necessary consequence of our models of the Big Bang. How could the smooth, primordial soup of the early universe ever evolve into the clumpy, structured place we see today? Gravity provided the answer, taking tiny, initial ripples in the density of matter and amplifying them over billions of years. Experts who mapped this structure, like Dr. J. Richard Gott III, describe these filaments as the cosmic backbone, the fundamental skeleton upon which galaxies are built. Observations have stunningly confirmed this vision. Projects like the Sloan Digital Sky Survey have painstakingly mapped the positions of millions of galaxies, revealing that they are not scattered randomly. Instead, they align along these invisible threads like luminous beads on a string. The environment within a filament is unique, a place of constant, gentle flow. The gas there is incredibly thin, far more diffuse than in any galaxy, yet it is pervasive. Gravity tirelessly pulls this raw material along the cosmic highways, directing it toward the hungry clusters waiting at the junctions. This intricate network is the primary delivery system for the universe, the conduit through which galaxies acquire the fuel they need to birth new stars and grow. It is this very process of cosmic nourishment that sets the stage for the next great mystery, the dramatic birth of entire galaxy families within this vast, guiding framework. These pristine rivers of hydrogen gas are the universe's ultimate creative engines. Within the dark matter filaments, vast reservoirs of ordinary matter begin a slow, graceful dance, gradually accumulating into the dense clouds that will one day ignite as glorious galaxies. This is the filament's primary role, serving as a cosmic nursery where the raw potential for entire galactic families first takes shape. Leading cosmologist Dr. Carlos Frank explains that the first structures to form after the Big Bang were not galaxies themselves, but these vast, interconnected filamentary networks. They acted as immense gravitational traps, their subtle pull funneling primordial gas into the nodes and intersections where the first stellar fires would eventually spark into existence. The entire process hinges on a cosmic sequence. Dark matter, unaffected by the pressures that buffet ordinary matter, is the first to clump together. It weaves the initial, invisible skeleton of the cosmic web. This dark framework creates deep gravitational wells, subtle dips in the fabric of space that begin to attract the flows of ordinary hydrogen gas. As this gas streams along the filamentary highways, it does not flow smoothly. It begins to cool, to fragment, and eventually to collapse under its own growing weight. These collapsing pockets become the seeds for the first stellar populations and the nascent cores of future galaxies. We see evidence of this ancient process even today. Observations of incredibly distant, high-redshift quasars often show that the vast clouds of gas surrounding them are aligned with the predicted directions of cosmic filaments. This is a fossil record of early accretion, a sign that these brilliant beacons were fed by cosmic rivers in their youth. The gas within a filament is not uniform, it contains slight variations in density. These tiny overdensities become the gravitational seeds for future galactic clusters, with the filament itself acting as a persistent feeding tube, continuously supplying fresh material to the growing structures. This continuous inflow is absolutely crucial. It is the reason many galaxies can sustain star formation for billions of years, preventing them from using up their fuel and prematurely quenching, fading into darkness. But this process also answers a deeper question about galactic diversity. What determines whether a cloud of gas evolves into a massive, red elliptical galaxy or a graceful, star-forming spiral? The rate and the manner of gas accretion from these filaments play a pivotal role. A steady, gentle flow along a filament might foster the ordered rotation of a spiral galaxy, while more violent, merger-driven accretion from multiple filaments could lead to the chaotic, spheroidal shape of an elliptical. The nurturing environment of a filament does more than just birth galaxies. It imprints upon them their fundamental identity, their size, and their ultimate structure, setting the stage for the complex relationships that define entire families of galaxies. Dark matter's gravitational embrace is what gives the cosmic web its enduring form. While we cannot see this mysterious substance directly, its presence is felt everywhere, weaving the invisible threads that bind the universe together. Think of dark matter as the fundamental framework, a cosmic skeleton that formed first, creating deep gravitational potentials into which ordinary matter could later flow. Groundbreaking research, like the pivotal work of Dr. Vera Rubin on galaxy rotation, revealed that the visible stars and gas we observe are merely tracing the edges of a far more massive, unseen presence. This dark matter does not emit, absorb, or reflect light, but its immense gravitational pull is the primary force sculpting the vast filaments we see today. Sophisticated computer simulations, such as the landmark Millennium simulation, allow us to watch this process unfold across billions of virtual years. They show countless dark matter particles responding only to gravity, gradually coalescing into an intricate cosmic web. The densest knots in this web become the great galaxy clusters, while the long, connecting tendrils form the filaments themselves. This dark matter scaffold emerged first, establishing the routes for the cosmic highways. Ordinary visible gas, the baryonic matter that makes up stars and planets, had no choice but to follow this pre-existing blueprint, streaming along the gravitational contours laid out by the dark skeleton. The properties of any given filament are a direct reflection of this underlying dark architecture. A region with a higher density of dark matter will weave a thicker, more massive filament, capable of channeling immense rivers of gas toward its endpoints. These colossal filaments, in turn, feed the birth of the most massive galaxy clusters at their intersections. Without this invisible scaffolding, the universe would lack its grand design. Galaxies would be scattered randomly, like leaves tossed in the wind, rather than organized into the luminous strings and clusters we observe. How then do we map something that is fundamentally invisible? We observe its profound effects. Through the subtle bending of light known as gravitational lensing, astronomers can trace the distribution of dark matter by watching how its gravity distorts the images of distant galaxies. The very motion of galaxies within and around filaments also betrays the presence of the dark matter halos that guide them. This stable, invisible framework does more than just create structure, it maintains it. Dark matter provides the gravitational glue that holds filaments together for billions of years, allowing them to act as persistent guides for galactic evolution. This enduring stability ensures that galaxies are not just born within this cosmic infrastructure, but that they continue to move along its predetermined paths, their journeys and interactions choreographed by the unseen hand of dark matter. Yet this journey is not a simple freefall. A filament acts as a galactic superhighway, channeling entire families of galaxies along predetermined routes toward immense gravitational hubs. Picture our own Milky Way not as a stationary island universe, but as a traveler on a vast cosmic road. We are part of the Laniakea supercluster, and astronomers have traced our motion along a filament, drawn toward the mysterious gravitational pull of the Great Attractor. This migration is a fundamental process. Galaxies experience a persistent tug from the colossal mass concentrated at the intersections of these cosmic threads, guiding them steadily from the sparse galactic countryside into the densely packed cities of galaxy clusters. Astrophysicist Dr. Mark Nairink notes that we can now map these velocity flows, observing coherent streams of galaxies moving together along these immense bridges. The filament provides a relatively safe passage compared to the empty voids. While the journey is long and gradual, the density of other galactic travelers is higher along this road, increasing the chances of encounters and interactions long before the final destination is reached. Sophisticated computer simulations reveal that a majority of galaxies which end up in clusters did not fall in from random directions. They arrived via these filaments, their motion choreographed by the invisible architecture of the cosmic web. This directed journey has profound consequences for a galaxy's life story. As it travels, a galaxy might gently brush past a neighbor, or even experience a major merger, events that can trigger brilliant bursts of new star formation or, conversely, begin to quench its stellar nurseries. The very structure of the galaxy, whether it remains a graceful spiral or is reshaped into an elliptical ball of stars, can be determined by the interactions it experiences on this cosmic highway. The filament does not just guide a galaxy's location, it actively shapes its identity during the voyage. But what happens when the journey ends? The exit from this galactic freeway and the entry into a dense cluster is one of the most dramatic transitions a galaxy can face, a moment of profound change that reshapes its future forever. A galaxy is a living engine that must constantly feed to survive, and the intergalactic filaments are its vital supply lines. These cosmic rivers deliver the cold, pristine hydrogen gas that serves as the fundamental fuel for star formation. Without this continuous replenishment, even the most brilliant galaxies would exhaust their internal reservoirs in a relatively short cosmic time, their stellar fires slowly fading into darkness. Astronomer Dr. Rommel Dave highlights a crucial distinction in how this feeding occurs. The mode of gas accretion, whether it is a smooth, steady inflow from a filament or a violent, chaotic merger with another galaxy, leaves a permanent mark on a galaxy's star formation history. The most elegant feeding mechanism is known as the cold flow. In this scenario, cool gas from the heart of a filament streams directly into a galaxy's halo, bypassing the hot gas that might otherwise heat it up. This provides a gentle, persistent trickle of new fuel, a delivery that can maintain a steady rate of star birth for billions of years. We see evidence of this process stamped across the distant universe. Observations from the Hubble Space Telescope have detected faint, extended coronas of gas around young galaxies, structures that are perfectly aligned with the predicted directions of cosmic filaments. These are the fossilized streams of ancient accretion, the direct imprint of filament-fed growth. The effectiveness of this cosmic nourishment depends heavily on a galaxy's circumstances. A lower-mass galaxy residing within a filament can often siphon this cold gas quite efficiently, sustaining its star-making for eons. In contrast, a galaxy that has fallen into a dense cluster faces a harsher reality. There, its gas supply can be brutally stripped away, a process that rapidly quenches its ability to form new stars. Yet even this accretion is not always a peaceful affair. When separate streams of gas flowing along different filaments collide, they can create immense shock waves. These events heat the gas to extreme temperatures, temporarily halting its ability to collapse and form stars. It is only after this agitated gas slowly radiates away its heat and cools down that star formation can reignite. This delicate balance between the incoming supply of gas and its rate of consumption ultimately writes a galaxy's destiny. A steady, regulated inflow often supports the ordered rotation of a star-forming spiral disk. But if the gas supply is cut off or overwhelmed by a sudden, merger-driven influx, a galaxy may rapidly transform, its star birth ceasing as it settles into the quiet, reddened existence of an elliptical. So how do galaxies avoid burning through their fuel too rapidly? They possess their own regulatory systems. Fierce winds from supernova explosions can eject vast quantities of gas back into intergalactic space. But even this expelled material is not always lost forever. The persistent gravitational pull of the filament can often recapture this gas, recycling it in a grand cycle of death and rebirth. This cosmic lifeline, the endless flow from the filaments, ensures that galaxies are not static islands. They are dynamic, evolving entities, their growth and transformation intimately woven into the larger scale movements of the cosmic web. The very spin of a galaxy may be a cosmic inheritance. Its rotation is not born in isolation, but is imprinted upon it by the vast filamentary structure from which it formed. Picture a spiral galaxy, its majestic arms tracing a delicate pinwheel in the void. The axis around which it spins often aligns in a specific, elegant relationship with the filament that feeds it, the disk of stars rotating in a plane parallel to the direction of the cosmic river. This remarkable alignment is a direct prediction of our most advanced simulations of the universe, and it is a prediction that has found strong support in our observations of the real night sky. The origin of this spin lies in the earliest moments of galactic childhood. It arises from what cosmologists call tidal torques, the gentle gravitational tug of war between neighboring clumps of matter as they slide past one another along the filamentary highway. These interactions, occurring over immense timescales, impart a specific twist to the collapsing cloud of gas, setting the entire future galaxy into a slow, steady roll. As leading astrophysicist Dr. Julio Navarro explains, the spin vector of a galaxy is like a fossil, preserving the memory of the large-scale cosmic geometry from which it was born. Studies of countless spiral galaxies reveal a telling statistical trend. Their disks are more likely to be oriented edge onto the nearest filament. This means if you could stand within the filament and look toward the galaxy, you would see it spinning like a wheel rolling along the cosmic road. This alignment is especially strong for the brightest and most massive galaxies, a clear sign that the process of acquiring spin is intimately linked to the process of acquiring mass from the filamentary flow. The mechanism is beautifully intuitive. As rivers of hydrogen gas stream along the gravitational contours of the filament and fall into the growing galaxy, they do not fall straight in. The geometry of the flow itself carries a specific angular momentum, a directional spin that is transferred to the galactic structure, setting its fundamental rotation. This is far more than a simple curiosity. The orientation of a galaxy's spin directly influences its future. It can affect how efficiently it continues to siphon gas from the filament, or it can change the dynamics of a close encounter with another galactic traveler, making a gentle passage more or less likely than a dramatic collision. When a galaxy sits at a cosmic crossroads where multiple filaments converge, the story becomes even more complex. Conflicting flows of gas from different directions can pull on the galactic disk in competing ways, potentially warping its shape or creating peculiar internal motions that betray this turbulent feeding history. By reading the spin of a galaxy, we are reading a chapter from its own creation story, a direct line back to the initial conditions that shaped it within the cosmic web. This subtle correlation is a profound clue, a hint that the largest structures in the universe leave their signature on the very rotation of the islands of stars they nurture. A galaxy's form is a direct reflection of its cosmic address. The graceful spiral and the featureless elliptical are not just different designs. They are products of a galactic environment, shaped by the invisible currents of the cosmic web. This relationship, known to astronomers as the morphology density relation, reveals a simple but profound pattern. Denser regions of space, like the cores of galaxy clusters, are overwhelmingly dominated by red, elliptical galaxies where star formation has long since ceased. In contrast, the sparse, lonely voids are home to isolated, often irregular galaxies. But what about the vast territories in between? This is where filaments reveal their true influence as the universe's great transitional zones. As the pioneering astrophysicist Dr. Alan Dressler observed, the environment exerts a powerful hand in determining a galaxy's fate, and filaments represent a crucial preparatory stage. Within a filament, a galaxy exists in a state of delicate balance. It is far denser than the void, ensuring regular, though gentle, interactions, yet it is not as brutally crowded as a cluster core. This intermediate environment allows for a continued, if sometimes disrupted, flow of gas from the cosmic highway. This persistent fuel supply is what helps maintain the star-forming disks of spiral galaxies, allowing them to retain their iconic structure as they travel. However, the journey along the filament is not without its perils. As a galaxy is channeled toward a massive cluster, it undergoes a process known as pre-processing. Long before it enters the chaotic core, the galaxy's character begins to change. The gravitational tides of the filament itself, or repeated, fast-paced encounters with other galactic travelers, can gently distort its shape. The tenuous gas within the filament, while thin, can exert a subtle pressure, slowly stripping away a galaxy's outer reservoirs of star-forming fuel. We see the evidence in galaxies that are still within the filament but close to a cluster. Their spiral arms may appear frayed and disturbed, and their rate of new star formation is often in decline. They are being transformed, their vibrant blue hues slowly fading to red. The filament acts as a cosmic preparatory school, gradually quenching a galaxy's stellar fires and reshaping its structure before the final, dramatic entry into the cluster. So why do some galaxies in filaments remain pristine spirals while their neighbors evolve into ellipticals? The answer is written in their individual journeys. A galaxy's initial mass and gas content set its resilience. Its specific path within the filament determines how many close encounters it will experience. A galaxy that travels a relatively quiet route might arrive at the cluster still a spiral, only to have its gas violently stripped away later. Another, on a more turbulent path through the same filament, might experience a series of minor mergers that steadily puff its stars into an elliptical shape long before it reaches its destination. This morphological transformation is a fundamental chapter in a galaxy's life cycle, a process guided by the architecture of the cosmic web. But the most dramatic changes are often reserved for the crowded intersections where multiple filaments converge, creating nodes of immense gravitational power. The grandest cities in the cosmos are born at the crossroads of these cosmic highways. Where multiple intergalactic filaments converge, they create a node of immense gravitational power, a hub that evolves into a galaxy cluster. These clusters are the true metropolises of the universe, containing thousands of galaxies all bound together by gravity. Their formation is not a sudden event but a continuous, hierarchical process orchestrated by the filaments that feed them. Advanced simulations like the Illustris TNG project show this growth in stunning detail. Over billions of years, filaments act as persistent conduits, funneling a steady stream of dark matter, galaxies, and most importantly, vast quantities of primordial gas directly into the cluster's deepening gravitational well. The arrival of this gas is anything but peaceful. As separate rivers of matter flowing along different filaments collide at the node, they create immense shock waves. The energy of these collisions is so tremendous that it heats the gas to temperatures of millions of degrees, causing it to glow intensely in X-ray light. This forms what astronomers call the intra-cluster medium, a seething, thin atmosphere that permeates the entire cluster and contains far more ordinary matter than all the galaxies within it combined. We can see this process at work in nearby clusters like Perseus. Detailed maps reveal that its position is not random. It sits at the nexus of several faint strands in the cosmic web, each one a delivery route for new material. The brilliant X-ray glow from its hot gas is a direct testament to the violent, energetic processes happening at this cosmic intersection. The environment within a cluster node is one of extreme dynamics. The density of galaxies is so high that close encounters and mergers become commonplace, dramatically reshaping galactic structures. Gravitational tidal forces pull and distort galaxies as they pass near one another. The behavior of the superheated gas itself becomes a dominant force, with some of it cooling and flowing inward in vast cycles, while other parts are reheated by powerful outbursts from supermassive black holes at the centers of galaxies. This intricate feedback loop, where accretion fuels black holes which then inject energy back into the system, is a key regulator of cluster growth. The very identity of a galaxy cluster, its total mass, the temperature of its gas, and the types of galaxies it contains, is a direct product of the filaments that built it. A cluster fed by several thick, massive filaments will grow into a rich, dense metropolis. In contrast, a node supplied by only a few weaker streams may remain a quieter, poorer group of galaxies. This accretion is an ongoing process. Clusters are not static relics. They are living structures that continue to grow even today, as new galaxies and fresh reservoirs of gas flow in along the persistent cosmic highways. This relentless delivery of material to the cluster core helps explain the intense activity often witnessed there. The compressing and shocking of incoming gas from multiple directions can trigger brilliant, short-lived bursts of new star formation. This same influx of fuel can also feed the supermassive black holes lurking in galactic centers, causing them to flare into active galactic nuclei, some of the most luminous objects in the universe. The node is the ultimate crucible, a place where the guiding influence of filaments culminates in the most dramatic transformations, setting the stage for the feedback processes that ultimately govern the life and death of galaxies on the largest scales. This cosmic filament is far more than a passive pipe. It functions as a dynamic regulator, a pressure valve within a vast galactic engine. The violent feedback from supernova explosions or the furious outbursts from supermassive black holes, known as active galactic nuclei, can blast gas clear out of a galaxy. Yet the surrounding filament profoundly modulates this process. As astronomer Dr. Megan Donahue points out, the environment dictates how these energetic feedback bubbles expand and interact. When a galaxy embedded within a filament experiences a colossal outburst, the ejected material does not expand in a perfect sphere. It meets resistance. The denser material surrounding the galaxy confines the explosion, forcing the superheated winds and radiation to channel outward along the path of least resistance, which is often the very axis of the filament itself. We see stunning evidence of this in observations of certain radio galaxies. Their colossal, jet-inflated lobes are not symmetrical. Instead, they stretch out for vast distances, perfectly aligned with the direction of the large-scale filament. as if the cosmic road itself is guiding the galaxy's exhaust. This directional feedback creates a ripple effect across intergalactic space. The outflowing energy heats the pristine gas within the filament, potentially raising its temperature enough to temporarily halt its collapse and starve neighboring galaxies of fresh fuel. Simultaneously, these winds carry a crucial cargo, heavy elements forged in stellar furnaces and supernova blasts. They seed the filament with metals, chemically enriching this primordial highway and ensuring that the next generation of stars born from its flows will have the building blocks for planets. This process creates a delicate balance. In the crowded core of a galaxy cluster, feedback is often tightly confined, creating a cyclical battle between heating and cooling. But within a filament, the lower density allows these outflows to travel much farther, their influence stretching across millions of light years to impact galaxy evolution on a truly grand scale. The filament also offers a form of cosmic recycling. Gas that is violently ejected from a galaxy does not always escape forever. The gravitational embrace of the filament can capture this material, allowing it to slowly cool over eons before eventually falling back onto the galaxy in a continuous fountain of death and rebirth. This intricate dance between internal violence and the external structure of the cosmic web is a fundamental form of galactic self-regulation. It prompts a deeper question about the very substance flowing through these channels. What is the true thermal state of the gas within these cosmic rivers, and how does its temperature dictate the ultimate fate of the galaxies it feeds? The gas flowing through these cosmic rivers is far from uniform. Peer into the heart of a filament, and you would encounter a complex, multi-layered medium, a mixture of temperatures and states that dictates its ultimate role in galactic growth. This is not a simple, cold river of hydrogen, but a dynamic sea ranging from warm, neutral gas to a hot, ionized plasma that glows faintly in X-rays and ultraviolet light. The thermal state of this filament gas is everything, because it ultimately determines how readily the material can cool, collapse, and ignite into new stars. As cosmologist Dr. John M. Shull describes, the dominant component is known as the warm-hot intergalactic medium, or WIM. This material exists at staggering temperatures between 100,000 and 10 million Kelvin, a state so energetic that its atoms are stripped of their electrons, creating a diffuse, ionized plasma. This very heat is what makes these cosmic arteries so challenging to observe directly. We cannot simply take a picture of them. Instead, we must rely on clever, indirect methods to trace their presence. One of the most powerful techniques involves using distant quasars as cosmic flashlights. As the brilliant light from a quasar travels across the universe toward us, it passes through these invisible filaments. Specific wavelengths of that light are absorbed by the highly ionized oxygen and carbon within the WIM, creating a unique fingerprint, an absorption line in the quasar's spectrum. The Hubble Space Telescope has identified many of these telltale signatures, providing some of the best evidence we have for this elusive component of the cosmic web. But what keeps the gas in this hot, ionized state? The energy comes from two primary sources: a persistent bath of ultraviolet radiation emitted by all the quasars and young galaxies in the universe continuously batters the gas, keeping its atoms ionized. Furthermore, as the gas itself flows along the gravitational contours of the filament, it does not move smoothly. It collides and creates immense shock waves, a process known as shock heating that pumps tremendous thermal energy into the medium. This creates a constant tug of war within the filament. While much of the gas is kept hot and diffuse, local pockets of higher density can rapidly cool by radiating away their heat. It is within these cooling pockets that the gas can condense into colder, denser clouds, the direct and pristine fuel that is eventually delivered to galaxies to form new stars. The overall balance between these heating and cooling processes is what regulates a galaxy's growth. If the filament gas is too hot, it becomes buoyant and cannot easily settle into a galactic disk to form stars. This delicate thermal equilibrium explains why some parts of a filament are detected in emission, glowing faintly with their own light, while other sections are only revealed in absorption, as dark lines against a brighter background. It all depends on the local density and temperature, which can vary dramatically along the filament's length due to gravitational interactions or violent feedback events from nearby galaxies. Observations from the Planck satellite, using a phenomenon called the Sunyaev-Zeldovich effect, have even mapped the thermal pressure of this gas in the spaces between colossal galaxy clusters, further confirming its pervasive presence. Understanding this intricate thermal dance is absolutely essential. It is the key to finally creating a complete map of the cosmic web and to accounting for all the ordinary matter in the universe, matter that has long been missing from our inventories. This quest to see the invisible drives astronomers to develop ever more ingenious tools, pushing the limits of our vision to illuminate the hidden architecture of the cosmos. Astronomers face a cosmic game of connect the dots on the grandest scale possible, tracing structures that are often invisible to our telescopes. To map the faint architecture of the cosmic web, they employ a brilliant array of detective techniques, each one revealing a different facet of these elusive filaments. One foundational method involves simply looking at where galaxies choose to live. Massive surveys like the Sloan Digital Sky Survey have meticulously charted the three-dimensional positions of millions of galaxies. When you plot all those points in space, a pattern emerges from the seeming chaos, a vast interconnected network where galaxies align along invisible lines. As Dr. Michael Strauss explains, scientists then apply sophisticated algorithms to this galactic map. These computer models, with names like the BISIS process, are designed to identify the underlying skeleton, statistically extracting the filamentary network and allowing us to measure its density, length, and connectivity. But this is only the first clue. To understand what flows within these cosmic rivers, astronomers turn to the universe's most brilliant beacons, quasars. The intense light from a distant quasar acts like a cosmic flashlight. As it journeys across the universe toward us, it passes through the diffuse gas of filaments. Atoms within that gas absorb very specific wavelengths of the quasar's light, leaving behind a unique barcode of dark lines in its spectrum. This forest of absorption lines, especially from hydrogen in its Lyman alpha state, provides a direct snapshot of the warm-hot intergalactic medium threaded through the cosmic web. Instruments like the Cosmic Origins spectrograph on the Hubble Space Telescope have been vital in decoding these subtle signatures. For the very hottest components of the filaments, we shift our gaze to X-ray vision. Telescopes like Chandra can sometimes detect the faint glow emitted by gas that has been heated to millions of degrees, particularly in regions where filaments are compressed between colossal colliding galaxy clusters. Another powerful technique relies on the afterglow of the Big Bang itself. The cosmic microwave background radiation, the oldest light in the universe, washes over everything. As this primordial light passes through a filament, the hot electrons within the gas give it a slight energy boost, a subtle distortion known as the Sunyaev-Zeldovich effect. Instruments like the Atacama Cosmology Telescope are exquisitely designed to measure this effect, creating a thermal map that reveals the presence and pressure of filament gas. Perhaps the most profound method involves using space itself as a lens. The immense mass of a filament, dominated by dark matter, warps the fabric of space-time around it. This warping slightly distorts the shapes of countless background galaxies in a process called weak gravitational lensing. By carefully measuring these tiny, systematic distortions, astronomers can trace the invisible dark matter skeleton directly, weighing the cosmic scaffolding without ever seeing it. Each of these techniques alone provides only a fragment of the story. Galaxy surveys show us the structure, Quasar absorption reveals the gas, X-rays detect the heat, and lensing uncovers the mass. It is only by combining all these different observational threads that we can weave a complete portrait of the cosmic web. The greatest challenge in this work is the sheer faintness of the filaments. Their low density and incredibly dim surface brightness push our most advanced telescopes and most complex data analysis to their absolute limits. A constant reminder that we are peering at the very edge of visibility. Yet with every new technological advance, the ghostly outline of the universe's largest structure comes into sharper focus. A hidden geography slowly being charted for the very first time. The cosmic web was not always the grand, defined structure we observe today. If we could rewind time to the universe's first billion years, we would find a very different scene. The initial state was one of remarkable smoothness, a near-uniform sea of matter and energy, punctuated only by the tiniest of ripples. These primordial fluctuations, imperceptible wrinkles in the fabric of space-time, held the entire blueprint for the future. As leading cosmologist Dr. Simon White describes, gravity was the patient sculptor that went to work on this smooth canvas. It began to pull matter ever so gently from the vast, empty regions we now call cosmic voids, channeling it into the faint, linear overdensities that were the infant filaments. This process, known as hierarchical structure formation, is the universe's fundamental building method, where small structures merge to form larger, more complex ones. In this youthful cosmos, the filaments were tenuous threads, delicate and sparse. They contained far less gas and were far more isolated from one another. The evidence for this early, diffuse network is etched into the light from the most distant quasars. When astronomers analyze the Lyman alpha forest at high redshift, they see a web that is less coherent and more fragmented than the robust networks surrounding us today. The gas flowing through these ancient rivers was also pristine, virtually free of the heavy elements that are commonplace now. This is because very few stars had yet lived and died to forge and scatter those metals across the cosmos. Over billions of years, gravity's relentless pull caused these filaments to evolve dramatically. They grew thicker and stronger, accreting matter from their surroundings and, in monumental events, merging with other filaments to form the massive cosmic arteries we now map. Sophisticated computer simulations like the landmark Eagle project allow us to watch this entire cosmic story unfold. They show the web becoming increasingly defined and interconnected as the universe ages, with filaments strengthening and the clusters at their nodes swelling in size. This evolution answers a profound question. Why do filaments appear more prominent in our current epoch? Gravity has simply had more time, nearly 14 billion years, to gather matter into these structures. While the universe's expansion continues, the initial rapid growth phase has passed, allowing gravity to sculpt the distribution of matter into this intricate, persistent lattice. The role of filaments has transformed alongside their physical growth. In the early universe, galaxies were utterly dependent on the cold, pristine flows from these filaments for their initial burst of growth and star formation. Today, the relationship is more complex. Feedback from generations of stars and black holes has chemically enriched the filament gas, polluting it with heavy elements that alter its cooling properties and change how future stars will form. This cosmic timeline reveals that the web is not a static stage, but a dynamic, evolving entity, one that has actively guided the growth of galaxies in different ways across the ages. The universe is a river in constant motion. Galaxies do not sit still, they travel, carried along the cosmic filaments by immense, invisible currents. This grand flow, known as the large-scale velocity field, is the most direct proof we have of the filament's gravitational power. Every galaxy moves with two speeds. One is the steady drift from the expansion of the universe itself, the Hubble flow. The other is its peculiar velocity, a subtle deviation caused by the local gravitational tug of nearby matter. By meticulously measuring these individual motions, cosmologists like Dr. Hume Feldman can perform a kind of cosmic cartography, tracing the underlying landscape of gravitational potential and identifying the massive filaments that act as the primary attractors. This is how we know our own Milky Way is not just moving, it is being pulled. We are part of a vast stream of galaxies all flowing toward the same mysterious gravitational sink, the Great Attractor, which is likely a colossal node where several of these cosmic rivers converge. These velocity flows are anything but chaotic. Redshift surveys, which map both the positions and the motions of millions of galaxies, reveal a stunning coherence. Galaxies move in concert, their paths elegantly aligned with the invisible axes of the filaments, as if they were all commuting on the same celestial freeway. The strength of this current is not uniform. A thicker, more massive filament woven from a greater density of dark matter creates a deeper gravitational well, pulling galaxies along its length with a stronger and stronger acceleration. This directed journey has immediate and dramatic consequences for the galaxies riding the current. The increased density and the coordinated motion within the filament raise the chances of close encounters. Galaxies can gently brush past one another, their mutual gravity compressing vast clouds of internal gas and triggering brilliant, short-lived starbursts. In more extreme cases, the flow can orchestrate direct mergers, collisions that utterly reshape a spiral galaxy into a featureless elliptical ball of stars. The traffic within this cosmic river is not perfectly smooth. If you observe closely, you will see that not all galaxies move at the same speed. Some race ahead while others lag behind, creating a velocity dispersion along the filament. This scatter is a telltale sign of the structure's history. An older, more dynamically evolved filament will have experienced more of these gravitational interactions over time, stirring up the motions of its galactic inhabitants and randomizing their velocities. What causes these cosmic traffic jams? The answer lies in the filament's own internal substructure. Just as a highway has areas of congestion and open road, a filament contains variations in its local density. Smaller knots of dark matter and groups of galaxies within the filament itself create their own miniature gravitational pulls, tugging on nearby travelers and creating subtle velocity gradients. This intricate dance of motions is more than just a spectacle. It is a powerful tool for weighing the unseen. By analyzing how galaxies flow, we can map the total distribution of matter, including the invisible dark matter that makes up the bulk of the filament's mass. These coherent flows validate the very idea of filaments as unified dynamical entities, the active conductors of a cosmic orchestra. They do not just guide galaxies from one place to another, they transfer energy and spin, imprinting their influence on the internal properties of the galaxies themselves, shaping their very essence from the outside in. The chemical legacy of a galaxy is written in the metals flowing through its cosmic supply lines. While hydrogen and helium are the primordial building blocks of the universe, every heavier element, the carbon in our bodies, the oxygen we breathe, the iron in our blood, was forged in the hearts of stars and scattered by their explosive deaths. This enrichment process is not confined to a single galaxy. It is a communal effort, and the intergalactic filaments are the distribution network that carries these heavy elements across the cosmos. The metallicity of a galaxy, its abundance of elements heavier than helium, becomes a living archive, a record of both its internal star-forming fires and the chemical history of the external gas it has accreted. As astronomer Dr. Jessica Work's research highlights, the gas surrounding galaxies often shows distinct metallicity gradients that align with the directions of cosmic filaments. This is a clear chemical signature, evidence that galaxies are constantly being fed streams of gas that are not pristine, but have already been seasoned with metals from other stellar systems. Consider the vast gas clouds orbiting our own Milky Way. Their chemical compositions are not uniform. Some clouds possess a lower metallicity, suggesting they are fresh, relatively unprocessed gas flowing in from the distant cosmic web. Others show a much higher metal content, indicating they are likely recycled material, gas that was once ejected from the Milky Way's disk or from a devoured satellite galaxy, and is now being recaptured by the galactic fountain, all channeled back along the same filamentary routes. The journey of this metal-enriched gas is a turbulent one. Within a filament, the efficiency of mixing these heavy elements depends entirely on the local flow. In regions of smooth, laminar flow, different metallicity streams can remain distinct for long periods, creating chemical gradients. But in areas of high turbulence, where flows collide or are stirred by galactic feedback, the metals can become thoroughly homogenized, creating a more uniform chemical soup. This has profound implications for the stellar populations born from this gas. A galaxy that primarily draws from a metal-poor filament will tend to form stars that are themselves metal-poor. Population: 2 stars that are ancient and long-lived. In contrast, a galaxy accreting from a pre-enriched, metal-rich flow will give birth to younger, population 1 stars like our Sun, which are rich in these heavier elements from their very inception. This chemical conveyor belt is most dramatically visible in the hearts of galaxy clusters. The intra-cluster medium, that superheated plasma between galaxies, is often surprisingly metal-rich. X-ray spectroscopy reveals abundant iron and oxygen, elements that could only have been forged in stars and then violently ejected. These metals did not appear by magic. They were carried into the cluster core over billions of years, transported along the filaments that fed the cluster's growth, a cumulative testament to the star-forming histories of thousands of galaxies. How does a galaxy maintain its chemical balance over cosmic time? It is a constant negotiation between internal production and external supply. A galaxy's own stars are continuously producing new metals and ejecting them, which would steadily increase its metallicity. Yet the continuous inflow of fresh gas from filaments, whether metal-poor or enriched, provides a diluting stream, a counterbalance that regulates this chemical evolution. This creates a vast chemical interconnectedness, galaxies sharing the same cosmic filament, drawing from the same gaseous reservoir, may develop surprisingly similar metallicity patterns over time. Their chemical histories become entwined, reflecting a common source and a shared journey along the cosmic web. The filament is far more than a gravitational guide. It is a chemical network, linking the fates of galaxies across millions of light years through the shared elements of life itself. These faint cosmic rivers carry an invisible force that shapes their very flow. Woven through the vast filaments of the cosmic web are immense magnetic fields, adding a powerful new dimension to their influence. While the origins of these intergalactic magnetic fields are still a subject of intense debate, they may have been seeded in the universe's earliest moments, and then amplified over billions of years by the same gravitational forces that built the filaments themselves. As astrophysicist Dr. Torsten Enslin has proposed, the shear flows within these structures, the way different layers of gas slide past one another, can stretch and strengthen these primordial magnetic fields. The resulting field strength is incredibly faint, just a few nanogauss, but its significance is magnified by the sheer volume it permeates. This magnetic presence fundamentally alters the behavior of the filament's gas. The field lines act as barriers, inhibiting the conduction of heat across them. This can create temperature anisotropies, meaning one part of the filament might remain significantly hotter or cooler than another, simply because the heat cannot spread evenly. We see indirect but compelling evidence for this. Observations of polarized radio emission from some galaxy clusters show faint extensions that reach out along the directions of connecting filaments. This alignment strongly suggests the presence of ordered magnetic fields channeling relativistic electrons through these cosmic structures. These magnetic fields also become cosmic highways for high-energy particles. When active galactic nuclei or starburst galaxies inject vast streams of cosmic rays into space, the magnetic fields within a filament can trap and funnel these particles over astonishing distances. As these cosmic rays travel, they contribute to ionizing the filament's gas, stripping electrons from their atoms. This ionization has a cascading effect. Free electrons act as catalysts, helping to form molecules and enhancing the gas's ability to radiate away its heat, which in turn influences how quickly the gas can cool and collapse to form new stars. In some regions, the magnetic field exerts its own pressure, providing a subtle support that can slow the gravitational collapse of gas clouds. This magnetic resistance might slightly delay the birth of a galaxy or even nudge its final morphology, influencing whether it becomes a disk or a spheroid. Detecting such weak magnetic fields in the near void of a filament is a monumental challenge, but astronomers have ingenious methods. One key technique involves studying the Faraday rotation of light from distant radio galaxies. As this polarized light passes through a magnetized filament, its angle of polarization rotates, and the amount of rotation reveals the strength and direction of the magnetic field integrated along its entire journey. Another method searches for synchrotron emission, the faint glow produced when relativistic electrons spiral along magnetic field lines. This magnetized environment introduces a beautiful complexity to the cosmic web, a constant interplay between gravity's relentless pull and magnetism's structured push. It influences how energy and matter are transported across millions of light years, adding a crucial layer to our understanding of how these cosmic arteries guide the evolution of entire galaxy families. The longevity of these cosmic rivers is a testament to a delicate gravitational balance. To truly understand their persistence, we must look at the vast, empty spaces they bridge, the cosmic voids that make up most of the universe's volume. These voids are not merely passive emptiness. They are active participants in the cosmic dance, their relentless expansion creating the low-pressure environment that allows filaments to stand out in stark relief. Filaments possess a remarkable stability because they are gravitationally bound along their immense lengths, their internal self-attraction fighting a constant tug-of-war with the expanding voids on either side. As void specialist Dr. Rien van de Wegeert describes, the dynamics are intimately coupled. As a void grows, it stretches the adjacent filaments, pulling them taut like strings on a cosmic instrument. Yet the gravitational glue within the filament resists this stretching, maintaining its structural coherence across billions of years. This equilibrium is why filaments can endure for so long, even as the universe itself expands. The matter within them is just dense enough to remain self-gravitating, creating a persistent highway in an ever-changing landscape. We see this interplay clearly around the Boots void, one of the largest known empty regions. Despite the void's colossal growth, the filamentary structures encircling it have held firm for eons, shepherding entire families of galaxies along its edges and preventing them from falling into the emptiness. The robustness of any given filament is determined by its mass per unit length. A thick, massive filament woven from a greater density of dark matter is far more resilient. It can sustain powerful rivers of gas and support a higher density of galactic travelers, acting as a mighty interstellar turnpike. In contrast, a thinner, weaker filament may be more susceptible to disruption. Voids do not just test the strength of filaments, they actively define the entire network. The pattern of voids determines where filaments can form, with these luminous strands typically outlining the empty regions in a vast cosmic foam. This void filament topology is a beautiful and precise prediction of our standard model of cosmology, the lambda cold dark matter model. and it is spectacularly confirmed by the large-scale maps created from galaxy surveys. This relationship answers a fundamental question. Why do these immense structures not simply collapse under their own gravity into spherical blobs? The answer lies in the support provided by the expanding universe and the sheer forces from neighboring voids. This external pressure acts against radial collapse, preserving their elongated, thread-like forms for cosmic epochs. The filament is not an isolated ribbon, but an integral part of a continuous cosmic landscape, its very existence and stability dictated by the emptiness it borders. This enduring infrastructure is absolutely essential for the long-term guidance of galactic evolution. It provides a reliable conduit for the flow of matter across the ages, a stable architecture that allows galaxies to grow and interact on predictable timescales. This cosmic stability, however, is not eternal, and it invites us to look forward, to ponder the ultimate fate of these grand structures in the far future of the universe. The grand cosmic web is not a permanent fixture. Its majestic filaments, which have guided galactic growth for billions of years, face a future dictated by an unseen force, dark energy. This mysterious pressure is causing the expansion of our universe to accelerate, a process that will ultimately overcome gravity's binding power on the largest scales. Over eons, this relentless expansion will stretch the very fabric of the cosmic web, pulling it apart thread by thread. As physicist Dr. Lawrence Krauss has explored, the gravitational bonds that currently hold galaxies together within these cosmic rivers will be tested to their limit. The proper distances between galaxies will increase so rapidly that their mutual gravitational attraction will no longer be able to maintain their connection. They will drift apart, becoming isolated islands in a rapidly darkening sea. Sophisticated simulations of this distant future reveal a sobering sequence. The first stage sees the filaments detaching from the great nodes, the galaxy clusters they once fed. These massive intersections will become unplugged from their supply lines, left as lonely monuments to a more connected age. The filaments themselves, now severed strands, will then begin to fray. The galaxies within them will steadily disperse, their coordinated motion along the cosmic highway giving way to a solitary, outward drift. Consider our own local cosmic neighborhood. In roughly a billion years, the filamentary bridge that now connects our local group of galaxies to the immense Virgo cluster may stretch beyond recognition. The space between them will have expanded so significantly that the gravitational influence and material flow between these structures will effectively cease. The role of filaments as galactic guides and nourishers will come to an end. The continuous flow of cold, pristine gas that has fueled star formation for eons will slow to a trickle and then stop entirely. Galactic interactions and mergers, those dramatic events that reshape galaxies and trigger starbursts, will become rare and then impossible. The universe will enter a state of profound isolation. For the galaxies themselves, this means an inevitable aging process. They will consume their remaining reservoirs of star-forming gas, and with no fresh fuel arriving from the cosmic web, their star formation will cease. The brilliant blue light of young, massive stars will fade from the cosmos, leaving galaxies dominated by the long, dim glow of red dwarf stars and the faint remnants of stellar cinders. The intrafilament gas, the warm, hot intergalactic medium, will become so diffuse that it can no longer cool and collapse to birth new galaxies. This cosmic quenching will be universal. Our ability to even observe this faint architecture will also vanish. The surface brightness of the remaining filaments will drop as they thin out, and the light from their gas will be redshifted by the immense expansion to wavelengths far beyond our detection capabilities. The cosmic web will fade from view, both in reality and from our perspective. This distant, quiet future underscores a profound truth about our present moment. The current epoch, where filaments are robust, active, and visible, is a special and transient phase in cosmic history. It is a uniquely vibrant era for galactic evolution, a time of construction and interaction made possible by the stable guidance of the cosmic web. While this end is unimaginably far away, it frames our current understanding of the universe as a glimpse into a dynamic and fleeting chapter of cosmic time. The universe weaves its web in many different sizes. From the faintest tendrils to the mightiest bridges, these filaments operate on a cosmic hierarchy, each scale playing a distinct part in the grand narrative of galactic life. On the smallest scale, we find delicate threads connecting individual galaxies within a local group. A perfect example is the Magellanic Stream, a faint river of hydrogen gas being gently pulled from the Magellanic Clouds toward our own Milky Way. This is a filament in miniature, a direct pipeline for transferring the raw fuel of star formation. When this gas collides with a galaxy's own reservoir, it can compress and ignite, sparking brilliant but localized bursts of new stars. This is galactic evolution in its most intimate form, a direct and ongoing transfer of material between neighbors. On an intermediate scale, we encounter the classic filaments of the cosmic web, the grand highways connecting entire galaxy clusters within a supercluster. The bridge between the Virgo and Coma clusters is one such structure, a river containing dozens of galaxies and immense reservoirs of hot gas. These are the primary conduits we have discussed, channeling a steady flow of galactic travelers and intergalactic fuel toward the dense urban centers of clusters. Their role is one of guidance on a grand scale, orchestrating the migration of entire galaxy families. Then there are the superfilaments, the titans of the cosmic web. Structures like the Sloan Great Wall stretch for hundreds of millions of light years, an immense backbone containing countless clusters and groups within its grasp. As Dr. J. Richard Gott III has described, these colossal formations represent the top of the cosmic hierarchy, the very last and largest structures to coalesce under gravity's patient pull. The physical nature of a filament changes dramatically with its size. A small tendril is highly susceptible to local forces. The gravitational tug from nearby galaxies can distort it, and fierce stellar winds from star formation can blow its gas away. Its gas is often cooler and more neutral, making it perfect for direct, cold accretion onto a galactic disk. In contrast, a superfilament is a realm dominated by cosmology and dark matter dynamics. Its gas is typically a superheated, ionized plasma, held in place by the immense gravitational potential of its dark matter skeleton. So why does this distinction matter so deeply? Because the impact on a galaxy's life story is entirely different depending on which filament it calls home. A small-scale filament directly feeds a galaxy, influencing its immediate star formation and chemical makeup through intimate gas transfers. A large-scale filament, however, sets the entire stage. It determines a galaxy's long-term migration path, the density of its neighbors, and the ultimate gravitational hub it will join. This multi-scale nature reveals a hierarchical cosmic ecosystem. Each level of filament operates in concert, from the local interactions that spark stellar nurseries to the global flows that build the universe's greatest cities. Recognizing this intricate variety is essential. It allows us to model the full spectrum of filamentary influence, connecting the fate of a single dwarf galaxy to the grand architecture of the entire cosmos. This cosmic recycling system operates on a scale almost beyond comprehension. The universe functions as a vast, self-regulating plant where the ordinary matter making up stars, planets, and us, known as baryons, is in constant motion. It is a grand cycle of death and rebirth, and the intergalactic filaments are its primary circulatory system, the great arteries through which this cosmic blood flows. This is the cosmic baryon cycle, a continuous loop where gas is drawn into galaxies, forged into stars, and then blasted back out into the void, only to begin the journey once more. Research by Dr. Jason Tumlinson into the circumgalactic medium, the extended gaseous halo surrounding galaxies, reveals that filaments are the essential channels for this entire process. They serve a dual purpose, acting as the route for the inflow of pristine, cold gas to fuel new stars, and simultaneously as the exit ramp for outflowing winds of metal-enriched material ejected by supernova explosions and violent black hole activity. Imagine a brilliant starburst galaxy, where thousands of stars are igniting in a furious firestorm. The resulting supernova winds act like a cosmic pressure washer, pushing vast quantities of gas out of the galaxy's disk. But this expelled material does not simply vanish into the emptiness. It is often channeled directly into the nearby filament, where it commingles with other flows. This ejected gas, now rich with heavy elements like carbon and oxygen, can then be swept up by the filament's gravitational currents. In a beautiful act of cosmic recycling, this same material may eventually fall back onto its original galaxy, or it might be delivered to an entirely different galactic system downstream. This cycle is the fundamental regulator of galactic growth. Without these powerful outflows, a galaxy would consume its fuel in a short, blazing burst of star formation, burning out quickly and fading into a quiet, reddened ember. Yet without the persistent accretion of fresh gas from the filaments, there would be no replenishment, no way to ever light those stellar fires again. The filament is the critical balance, acting as both a reservoir for storage and a mixing zone for different types of gas. Within its immense volume, primordial hydrogen from the dawn of time converges with metal-polluted exhaust from galactic centers, and superheated plasma mixes with cool, dense clouds. The effectiveness of this recycling is dictated by the filament's own properties. A denser filament with a stronger gravitational grip is far more efficient at retaining this ejected gas, holding it close so it can cool and eventually fall back onto a galaxy. In the crowded environment of a galaxy cluster, this entire cycle is amplified to an extreme. Filaments relentlessly pump gas into the intra-cluster medium, the superheated plasma between galaxies. Under the right conditions, this gas can radiate away its heat and flow back into the cluster's central galaxies in vast rivers known as cooling flows, though this process is often violently disrupted by feedback from supermassive black holes. How do we actually measure the baryons flowing through these invisible rivers? Astronomers rely on a powerful combination of techniques. Absorption line studies from distant quasars detect the faint imprint of filament gas. X-ray telescopes chart the emission from its hottest components, and observations of the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background, map its thermal pressure. Together, these methods reveal that a significant portion of all the ordinary matter in the universe resides in this warm, hot, intergalactic medium, threads of ionized plasma woven through the cosmic web. This grand baryon cycle demonstrates that no galaxy is an island. Each one is an open system, intimately linked to its large-scale environment by these filamentary conduits, which enable the continuous exchange of matter and energy across millions of light years. This dynamic interplay between the galactic and the cosmic sets the stage for understanding how these flows ultimately determine the specific fate of different types of galaxies. For the smallest galaxies, the cosmic web is a stage of both opportunity and peril. Dwarf galaxies, the faintest members of the galactic family, are exquisitely sensitive to their filamentary surroundings. Lacking the immense gravitational pull of their larger cousins, they cannot easily attract gas from great distances on their own. Their survival hinges on the gentle, persistent flow of the cosmic rivers. As astrophysicist Dr. Elena Donghia's work reveals, sophisticated simulations show a clear pattern. Dwarf galaxies residing within filaments can sustain their star formation for significantly longer periods than their isolated counterparts adrift in the vast cosmic voids. The filament provides a steady, if modest, trickle of hydrogen gas, a lifeline that prevents these small stellar systems from consuming their internal fuel and fading into darkness too quickly. We see this dynamic playing out in our own celestial backyard. The Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, are not merely floating in empty space. They are embedded within a faint filamentary structure, a cosmic current that is guiding their motion and delivering subtle streams of gas. Their recorded star formation histories are not smooth, but instead show distinct bursts of activity, brilliant flashes that are likely correlated with gravitational interactions and gas compression events as they travel along this filamentary highway. Yet the very structure that nourishes them also sets a dangerous course. This filament is channeling them directly toward the immense gravitational well of our Milky Way. As these dwarfs journey along this path, they experience intense forces. Powerful tidal gravity begins to pull them apart, stripping away their outer layers of stars and dark matter. Simultaneously, they plunge through the Milky Way's own extended halo of hot gas, a process known as ram pressure stripping that acts like a fierce cosmic headwind, violently blowing their remaining star-forming gas out into space. This transformation, this pre-processing within the filament, is a primary reason why so many of the dwarf satellite galaxies found around large galaxies like our own are quiet, gas-poor, and no longer forming new stars. Their vibrant blue stellar nurseries were quenched long before they completed their final approach. The low mass of dwarf galaxies makes every bit of gas critically important. Even a small accretion event from the filament can cause a dramatic spike in their star formation rate. This leads to an episodic life, a history marked by brilliant, short-lived bursts of stellar birth separated by long, quiet periods of dormancy, rather than the continuous, gentle activity seen in larger spirals. So why do some dwarf galaxies within filaments remain gas-rich while others are completely stripped bare? The answer is written in their individual trajectories. A dwarf's specific orbit within the filament and its distance from massive gravitational neighbors are the deciding factors. Those on radial orbits, falling directly toward a massive galaxy cluster, are far more likely to be depleted of their gas. In contrast, a dwarf on a more stable, circular path within the filament, or one that remains in the outskirts far from major hubs, has a much better chance of retaining its gaseous reservoir and continuing its slow, steady star formation. The filament thus acts as both a nurturing lifeline and a pathway to destruction, a dual nature that highlights the complex and often unforgiving influence of the cosmic web on its smallest inhabitants.